All right, so let's begin. And so last time around, we were looking at this operator formulation of 2D CFT. Oops, sorry. So we're looking at the operator formulation. And what we said was that, we had already, we were always looking at we have been so far looking at CFTs through word identities and OPEs. And OPs were implicitly always inside correlation functions, so we did not use any operator formulation. And what we had was everything was basically derivable from path integrals. But it turns out that having a notion of Hilbert spaces and operators becomes very useful for CFTs as well. And for that, what we first did was, when we want to speak about some sort of operator formulation, we need to we need to distinguish a sort of time direction. In a usual Lorentzian spacetimes, that's always going to be there because the time direction comes with a minus sign in the metric. And but when we're looking at Euclidean spacetimes, it's not very apparent what exactly one should do. So in order to make a distinction between space and time in the Euclidean setup, what we did is we took our theory to be defined on a cylinder. On a cylinder, the spatial direction is what we would actually look at as being identified, and the time direction runs from minus infinity to plus infinity. So the distinction between a compact direction and a non-compact direction is very clear in this case. So so if we were to define the field theory or the CFT on the cylinder, then so our equal sort of time slices are given by these. So so there is a natural distinction between what the space direction is and what the time direction is. The space direction is identified, the time direction is not. Now what we do is, if we were to move on to the plane like we have been doing, so there is this explicit map between the cylinder and the plane. And what happens is that this exponential map maps minus infinity in the time direction in the cylinder to the origin. So if you were to think of things, if you were to think of something which is, sort of operators or states at minus infinity, which is sort of like the usual notion of maybe in states. So so you remember in a quantum field theory, with the things that you have done earlier, you defined in states and out states. In states were defined at minus infinity, t as minus infinity, and out states were t as plus infinity, and they come in between and interact and so on and so forth. So what happens is that in that case, so minus infinity is sort of mapped to the origin out here. So what we will see later, so if we have an operator in that sense, which is equivalent to a state in this CFT language as well, it sort of means that it's being inserted at the, so if this is at t equal to minus infinity, equivalently on the plane, this operator is inserted at the origin. So this is the very nice thing about this mapping from the cylinder to the plane. And the equal time slices, as you go forward in time, this sort of point becomes larger and larger circles. And so the difference between so if you have two time slices t1 and t2, with t1 being earlier than t2, these will be mapped to two circles here, concentric circles with increasing radii. So what happens is that when you want to do something like this, so this was our sort of in state, if you wish, the thing that I was harping about earlier. is that when you're looking at an asymptotic in state, you actually need to insert this particular operator at the origin. If you were to act it on this, I mean on the vacuum, so you need to insert it on in the origin. So the other thing that I was saying is that these were so before I go on, yeah, so I will go to say a few more things about how to I mean conjugate things, but just to remind you of something that we did later, was this radial ordering. And the time ordering, in a sense, as we were seeing before, is replaced by something called radial ordering. And so this mapping that we had earlier, this makes it clear that if you were to time order things on the cylinder, on the plane, these will actually be radially ordered. Okay, so that was the thing that I was trying to get to. But we also saw other things, like we had defined these in states, and equivalently you would want to also define out states. So for that, in a sense, one needs to define an inner product on this Hilbert space. And we defined this as the following. This at first looked a little weird, but we saw that, okay, so somehow my things are not moving yet, are they? I'm sorry, let me just try this once more. Okay, if you guys can't hear me or can't see the screen, just let me know. Huh? It seems that my internet is not great. Okay, hopefully you guys can see my screen again. Hello?
No, sir, that's not it.
It was strikeout. Well,
Sorry, I mean, I can't seem to go forward or back here. Just give me a second, please. Sorry, my internet is very bad for some reason today. I guess you guys can't see it yet, right? Oh, this is very irritating.
Yeah, we cannot.
Yeah. Seems that this is just stuck for some reason. Yeah, I know my network is a bit weird today. This is a very, very irritating thing.
Maybe you can switch off the video and then try
Yeah,
to
yeah,
share
I
or
can
something,
do
because
that.
like
Yeah, it's
then the bandwidth
eating
is
up.
very
Yeah,
low.
yeah, eating up my bandwidth for some reason. But it's not even letting me, showing me any share screen options. Okay, now maybe, yeah. Uh, is it moving? Yeah, it is moving again. All right, very good. So with that interruption, um, so I was just saying that last time we also looked at what the Hermitian conjugates were, and then we saw what was happening was we had this priori weird looking way of trying to relate what phi dagger was to phi, and that also involved these factors of z in front. And it seemed that you also changed the space time coordinates, which is a little unfamiliar from the usual Minkowski perspective, because Hermitian conjugation in Minkowski spacetimes does not affect these coordinates. But if you were looking at Euclidean spacetimes, as we argued last time around, t was equal to it. So the fact that t remains unchanged means that tau here has to go to minus tau under conjugation, and that led to this. Especially z going to 1/z bar. These factors that we had, these prefactors that we had in front out here could be justified when you try to look at what the sort of inner product with this out and in was. There we saw in order to make sure that this did not depend on these coordinates, we had to have this extra prefactors in front, which sort of cancel it out with the 2-point function, the thing that you get from the 2-point function. So that was one thing, and then we sort of looked at the mode expansions, the LoRa modes of these fields. It was very similar to what we have for the usual. So there should be a minus somewhere as well. Yeah. So it was similar to what we had for the usual. Complex analysis, except for the fact that we also have these z bar modes. Okay, so if you have this function, so we are doing a sort of LoRa expansion of this, not only in z's but also in z bars, and so that's what we did. And we also saw that the Hermitian sort of conjugation here led to the fact that this phi dagger had to be equal to phi with the mode numbers with some extra signs. So that's what we found. And I told you a little bit about this radial ordering. And then we had this very important thing of how we linked up this contour integration with the brackets, with this commutator brackets. I've not put this up on the website yet. I will try and do that soon. So let me again just briefly remind you of what this is. So if we had an integral which was the following, and which was in dz az into b omega, where this contour circles anti-clockwise around omega. This particular thing has operator meaning as long as it's radially ordered. Okay. So, accordingly, what we will do is that we will split this into two circles, two contours, and so which will be going in opposite directions, and these can be so what we will do is we will deform this into this subtracted from this guy. So now, this is equivalently a circle which is a little larger, and this is equivalently a circle which is a little smaller. So one includes this point omega, and one does not. And we can split this up. So the radial ordering in that case means that the first integral around C1 has AZ into B omega. The second one, which is around C2, has this reversed. So this, in a sense, it defines what this defines the fact that this is going to be related to this commutator bracket, where A is given by the field integral of AZ dz. Okay, so this was nice, and the fact that if we had two of these guys, A and B, which were defined by the integral of z and integral of az and integral of bz, then the commutator of AB was given by this thing. So you did two of these sort of contour integrals now. So these two equations, 4.11 and the previous equation 4.9, related OPEs to commutator commutation relations, and allows us to translate from the statements of symmetries that are contained, that symmetries of the OPE and so on, into things which were in operator language. And the prime example of this we saw was when we applied this to the LLOP. So what did we do? We expanded TZ and T bar Z bar in LoRa modes again. Here you are so that's, and we tried to calculate what the commutators between these L, for example, just these LNs are. So you see, this is very similar to what we did earlier. Now you want to calculate this the commutator of two such guys which are under integral signs. And what we did is we went through the analysis, and we used the OPE here. And once we use the OPE, if we went through our way of defining this, we saw that we ended up in in the Virasoro algebra that you had seen earlier. It's important to point out that this sort of term, this central charge term, which came with the piece that made T a non-primary field, was actually responsible for what I had previously said was the central extension of the Witt algebra to the Virasoro algebra. So this was where we ended last time. Okay, this was rather a long revisit of what we did last time. So so let me quickly ask you if there are any questions regarding this. Is there something not clear? If not, I'll try and go ahead a bit more. Okay, does not seem to be. So let's just state now a few basic facts about the Hilbert space of a CFT. Now, the vacuum state, what we are going to be saying is going to be defined is going to be something which is invariant under global conformal transformations. Okay, so what does that mean? It means that L0, L plus minus 1, and L0 bar, L plus minus 1 bar are going to be, annihilated. So these are going to annihilate this particular vacuum state. Okay, so this essentially fixes the ground state energy to be equal to 0. And you can equivalently look at it as saying that this is Tz acting on 0 and Tz bar acting on 0 have to be sort of well defined in the limit z bar going to 0. So you can sort of move around between these all of these relations. So what does this imply? If you look at Tz and Tz acting on the ground state equal to 0 and T bar Z bar acting on the ground state equal to 0, this implies that all Ln's and Ln bars where n is greater than equal to -1 acting on this ground state has to be equal to 0. Okay. This in itself includes the sub condition that the ground state is invariant under the global conformal group, and it also implies that Tz, if you're looking at the 1-point functions, Tz and T bar Z bar, in the vacuum there's also 0. Okay, so this is reasonable and straightforward. What else? So what we want to sort of figure out is that, when the primary states act on the vacuum, I mean, when you look at some primary fields and you act on the vacuum, they create asymptotic states. So let's see this. So let's look at the I mean, what the commutator of L with phi is. So this is, again, so this is if I can get this is again gone, is it? I can mark it here, but I can't see it here. Oh, it's becoming impossible. Yeah, all right. Let me say this in words, and then we'll see if we can fix it again. So ln acting on this phi. So what is happening is that, you look at the OPE of this, and once you look at the OPE, you see that there is this h phi term, and there's this, I mean, del phi term, and you have this integral, and so once you do the integral, you end up with something which is, yeah, okay, now it's back on again. So you get an expression h of n plus 1, uh, omega n into phi and omega n plus 1, I mean, del phi. Okay, notice that if you put, I mean, omega and, I mean, omega bar equal to 0, then okay, let's first put let's first put Ln is equal to 0. So that would mean what? That would mean L naught acting on phi. Okay, let me try and write this. So that will mean L naught acting on phi gives you h, n plus 1 is there, omega is equal to 0, phi of omega and omega bar, plus n is equal to 0. So this is omega del phi, right? So that is what you would get. So this is also at omega bar. So let me just suppress these other indices here for the moment. So what you get is this. Now, if you put, I mean, omega equal to 0, this term drops off, right? So now what you see is, if you were to define uh, define this h in the way that I have h bar as phi 0 acting on the ground state, then you see that L0 h bar is equal to, so whatever, L0 h bar is just h of h bar. Okay, is this reasonably clear? I hope it is. So all you're doing is taking the OPE, finding out what L is, and you're just figuring this whole thing out. So let me. Okay, so that's what this is. So once you are going to define h bar as phi naught acting on the ground state, then you can very clearly see that L naught acting on h bar is h bar, L naught bar is h bar of h bar. And again, going back here, what you see, if n is so if you are going to put something where n is not equal to, so n is greater than 0, then all of these terms have these, I mean, factors of I mean, omega. And when, I mean, omega goes to 0, this just means that this whole thing will be equal to 0. Okay, so what we see is that for primary fields, what we see is this always holds, and also Ln and ln bar acting on this HH bar is equal to 0. Okay. All the excited states above this HH bar can actually be obtained by operating with the, ladder operators. So for example, what can we do? What are these ladder operators? Ladder operators are things that are going to increase the weight. So let's expand this phi of omega in modes. And if you do that, you'll find that when you take the bracket of ln with phi m, this is going to give you a form which is like this. So as a special case, if you're looking at phi naught, if you're looking at L naught, then you'll see that the weight actually is it actually will decrease. Okay, so so this weight is minus of something. Okay, so it means that with each application of phi minus m, for example, the dimension of this state is going to increase by m. So if there was something which had so if there was something which was phi, and you hit it with phi of minus m, then this object that you're going to have is going to, if this had a weight h, then this particular state will have a weight have a weight uh, the weight of this is going to be h plus n. So these guys will increase. So the weights are going to be increased by each application of phi minus n. So these are raising operators. Okay. Similarly, you can also raise by trying to look at L of minus m. So just by looking at what the Virasoro algebra is, you can read off that L naught with L minus m actually will raise the weights. So this is something that I urge you to do. So for successive, successive, you can just apply these successively on this, state H, and you can build excited states. Okay. So, I've written some psi down out here, which is all of these L minus KIs acting on H. So if the weight so the weight of the state H is H, so the weight of the state psi will be H plus K1 plus K2 plus up to Kn. Okay. So all of these, as you can see from here, will add something which is which is the label minus times the label here. So this is going to add K1 plus K2 plus dot 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 up to Kn. This sum of K1 up to Kn is called an integer big N. And all of these states psi are called descendants of this asymptotic state H. And this integer n is called the level of this particular descendant. Okay, very good. So the number of distinct linearly independent states at a level n is clearly going to be the partition of the number n. Okay, so for example, let me just write this down here. So for example, if you're looking at, or maybe let's take another page, and so as I said, if you have the psi which is L minus K1, L minus K2 dot 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 L minus Kn acting on H, and so as I said, K1 plus K2 plus dot 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 plus Kn is something that we call N. So let's look at a level n, level n equal to 1. So n equal to 1 means you just have, minus 1. So K1 has to be equal to 1. So this is one of these guys. So n equal to 2 would mean what? N equal to 2 would mean you could have a state like L minus 2 acting on H. But you could also have something which is L minus 1 squared acting on H. So So n equal to 3, what could that be? It could be L minus 3 acting on H. It could be L minus 2, L minus 1 acting on H, or it could be L minus 1 cube acting on H, right? So all of these three things are allowed. Similarly, so you see here, this is 1. Here, this is 2, and this is 1 plus 1. Here, this is 3. This is 2 plus 1. This is 1 plus 1 plus 1, right? So if you have so this is clearly, I mean, so you can go up to level 4 if you wish. Then you'll have L minus 4 acting on H, L minus 3, L minus 1 acting on H, L minus 2 squared acting on H, L minus 1 to the 4th acting on H, right? And yeah, do we have something else? Yes, we do. L minus 2, L minus 1 squared acting on H. So you see, these are again the number of ways that you can partition 4s. 4 can be 4, or it can be 3 plus 1, or it can be 2 plus 2, or it can be 2 plus 1. Sorry, let me. Or it can be 2 plus 1 plus 1, or it can be 1 plus 1 plus 1 plus 1. Right? These are all the ways that you can partition 4. So this is clearly Pn. So the partition of the, I mean, partition uh, of the number n basically. So the distinct linearly independent states at a level n is clearly the number Pn, which is the number of partitions of the integer n. This is something that we will see, that this can be this is something the generating function for this partition of numbers is 1 over q, where this is the Euler function. You can check this, and we'll find that this is actually useful later on. All right, so as I write here, the effect of conformal transformation on a state by acting on it with is obtained by acting on it with a suitable number of LMs. The subset of the full Hilbert space that is generated by this asymptotic state H and its descendant is closed under the action of the Virasoro algebra. This hence forms a representation of the Virasoro algebra. You can more sort of correctly say that it's a module. This subspace is called a Verma module, and we will have much more to say about this as we go ahead. Okay. All right. So that was that. Let me just actually delete this. Give me a second. Okay. Now we come to something a little formal, but let's do this. I mean, I was sort of debating whether I want to take you through this.
Sir?
Yes, yes,
Yeah, so in the last slide,
yeah,
the Euler function that you have written,
yeah.
it also takes into account the different orders in which else act, right? I mean, the partition function should not take into account the order in which else
That
act,
is
right?
right. That is right. So the point is, this is the partitioning of of a number, right? So
Yeah.
unfortunately, I just erased that. What I was trying to do. Let me let me just do this. So remember that there is you could have a state which looks like L. So let's look at L minus. So let us look at level 4. Okay, right? Uh, and this is so, for example, as I said, you could have L minus 4 acting on H bar. or let's not write h bars here anymore. You could have L minus 3, L minus 1 acting on H. You could have L minus 2 squared acting on H. You could have L minus 1 squared, L minus 2 acting on H. L minus 1 squared, yeah. And you could have L minus 1 to the fourth acting on H. Now you see that I'm not writing down something like L. So I've written down L minus 3, L minus 1 acting on H, right? But there could be another state, L minus 1, L minus 3 acting on H. This is very slow for some reason. Yeah, it says my internet connection is unstable. So you see that I am writing this. This is very irritating. So okay, let me try and say it in words. So you are seeing that I'm writing so L minus 3, L minus 1 acting on H, but I do not write L minus 1, L minus 3 acting on H, because these two are, I mean, just clearly, clearly just related, right? So if you are looking at, what the Virasoro algebra is, then L minus 1. So if you have a state, these are not going to be linearly independent, right? So if you have L minus 1, L minus 3, you could always write it as L minus 3, L minus 1, and L4, L minus 4. Sorry, this is horrible today. So are you guys able to hear me? Hello?
Yeah, somewhat.
Yeah, I know this is a very bad day today. Okay, let me try and do something. Let me sort of switch my internet on and off. And okay, it seems that it's back on again. Is there no? So let me switch my internet on and off, and let me just be back, because this is becoming horrible. Okay, just give me 2 minutes, guys. I mean,